Hey everyone, welcome back to CS 2040S. Let's get started. Okay, so as you see up here, I've been asking people what the hardest part of this class has been so far this semester. I see a lot of votes for Java. Yes, Java is hard. It is hard to learn a new programming language. Java is particularly tricky in the sense that there are all sorts of ins and outs. But I hope now, as we get to the end of week 3, everyone is slowly figuring it out. So everyone's slowly getting their Java legs under them. Between this class and 2030S, you should be seeing a lot of Java this semester. And so soon you are all going to be Java experts. Okay. And to the extent that you do still need Java help, that's great. Tutorials start this week. Your tutors are a great resource. Okay, what else do people have people found confusing so far? There is another comment on typing on Zoom, on chat on Zoom. So let me again ask you during class, please try to refrain from typing on Zoom chat unless you have a question for me. Please take your chatting to Discord or Telegram or your favorite alternate chat service so that it does not distract people. If you have a question for me, feel free to include it on chat. If chat continues to be distracting, I'm going to just disable it altogether, but that would be unfortunate. Okay. What else? I see a bunch of people say the most confusing part has been the Find the Spies optional contest. Excellent. That is a hard problem. I will post something on Coursemology in a little bit after, when the contest is over, explaining a little bit more about that. And I see, in fact, that someone just posted a link on the chat that has a bunch more details about the Find the Spies problem. Okay. What else? What else have people found hard so far? How to write the most efficient algorithm. Wonderful. That's a great thing to be confused by because that's exactly what we're going to be thinking about for the next several weeks. And I see lots of other issues on here, other things people find confusing. Again, to the extent that you are still struggling with certain things, please take advantage of tutors, ask questions in tutorial, come to tutorial with questions in mind of very specific things that you don't understand, and your tutor will explain them to you. Okay, good. So that has been enlightening to see what people are struggling with. As the semester goes on, please continue to let me know what's hard, what's easy, and how things are going. I'll ask this question a few more times this semester so we can see how things are going. Okay, one sec. Let me see if I can get PowerPoint shared here. 1 second. Here we go. Excellent. So we are on to the regular part of class. What are we doing today? Well, last time we were talking about sorting, bubble sort, selection sort, insertion sort, and merge sort. We were talking about the properties of sorting, so running time, space usage, stability, when is insertion sort fast, when is insertion sort slow, and so on. Okay, so that was last time. Another thing coming up today, problem set 3 is going to be released. In problem set 3, your job is to become a sorting detective. Okay, you have run across 6 suspicious sorting algorithms. Your job is to investigate the mysterious sorting algorithms and identify each of the sorting algorithms. One of them, though, is not who it claims to be. One of them is Dr. Evil and will not sort properly. It is your job to identify Dr. Evil along with each of the honest sorting algorithms. Okay. Now, the thing is, as part of your investigation, you must focus on the properties of the algorithms, on the asymptotic performance, on questions of stability, performance on certain special inputs, the asymptotic performance on special inputs, and so on. Okay, so if you give an answer about absolute speed, saying, this one's fastest, it must be bubble sort, well, you're wrong for several reasons, but that is not, even if you are correct in your identification, that is not an acceptable answer. Okay, so if you say things like, it ran the fastest, it must be QuickSort, or I compared the speed of A and B was much faster, so it must be insertion sort. These are not good answers. Your answers must be due to the asymptotic performance, due to things like stability, due to the properties of the algorithm, not due to any absolute performance numbers. Okay, great. So problem set 3 will be released and you will find it on Coursemology. Wonderful. So what are we doing today? Today we are talking about more sorting. Last time we talked about MergeSort, and I'm going to say a few more words about MergeSort, in particular space analysis, and then we're going to go on to QuickSort. Okay, we'll talk about QuickSort for the rest of today. We'll finish talking about QuickSort on Tuesday, and then we'll wrap up sorting on Tuesday. Okay, that is the plan. Wonderful. So just a recap, we're talking about sorting. We have some input that is an array of words and numbers. We are trying to produce an output that is a permutation of the input in sorted order. Excellent. The last thing we talked about was MergeSort. Okay, MergeSort is a wonderfully simple and elegant divide and conquer algorithm. You start out by first sorting the left and right halves recursively, and then the only interesting part of the algorithm is merging everything together. Okay, this was MergeSort. This was sort of a picture of what MergeSort is doing from a top-down perspective, right? We start off with some array, you divide it up into two pieces, you divide those into pieces, you divide those into pieces. Eventually, you have a whole bunch of individual pieces, and you start merging and merging and merging until you get to a complete array. Okay. There is, of course, an alternate way of thinking about MergeSort, which is the bottom-up way to think about MergeSort. Okay. So when you're thinking about bottom-up MergeSort, you imagine you start out with your whole array here, which is the thing that you want to sort. Okay. And maybe in your first pass through the array, what you're going to do is you're going to merge pairs of things together. So we start out by merging 15 and 7, and we get 7 and 15. We start out by merging 2 and 9, and 6 and 12, and so on. So we do each of these pairwise merges, and so on. Great, now we have an array with a whole bunch of pairwise sorted elements. Well, let's do another set of merging. So again, we can first merge 7 and 15, 2 and 9 using our merge routine and get this red sorted list. And then we can merge these, and so on. Oop, I don't know why we have 2 arrows over here. We don't need this extra arrow. And so on up the line, okay? If you think about this a little bit, you'll realize this is exactly identical to MergeSort, right? This is the exact same thing as MergeSort, except that we're not looking at it as a divide and conquer top-down algorithm, but a bottom-up iterative algorithm, where in each iteration you do a single pass through the array, and in each of those passes you merge a whole bunch of pairs of things. A nice coding challenge, if you're looking for one, is to implement this type of iterative bottom-up MergeSort. Same algorithm, but a slightly different coding challenge. Okay, good. So what I really want to talk about now, though, is the space complexity of MergeSort. I think I asked this as a question at the end of class last time, is how much space is allocated during a call to MergeSort. Okay, and what I really care about is I want to know how much space is allocated in total, right? We're analyzing algorithms here. I don't want to analyze Java. I don't want to worry about how the Java garbage collector works. I don't want to deal with any of the nonsense that is Java. I want to just focus on the algorithmic question of how much space is allocated during a call to MergeSort. Okay, good, let's do that. And of course, the key subroutine we're going to have to think about is merge, right? Anytime you look at MergeSort, the only thing that really matters is the merge routine. So the first thing you'll notice if you look at the merge routine here is that, well, whenever you call merge, you're going to have to allocate this array of size n, right? Every time you call merge, you allocate a new array of size n to store all the items that you merge, okay? Or another way of thinking about it, let's go back to our pseudocode here, is that, well, whenever we do a merge sort, we get returned a new array x containing half the items that were sorted, and we get back another new array y that's half the items we've sorted, and we call merge, which returns a new array of size n. Okay, so let's think about what goes on here. Well, this is sort of theta 1 space. There's or nothing really happening here, no space being allocated here. Here we have 2 recursive calls, each of which are going to allocate some amount of space. It's doing a sort of size n over 2. Okay, and then here in merge, we're allocating n new space, right? We're allocating a new array of size n to do this. Okay, great. So let's so what does that end up being? What do you get if you solve this recurrence? Let's hop over to Archipelago and let's put in the answer. I talked to the Archipelago people about the performance. We'll see if it is any better today. They are unfortunately running on a shoestring budget, so they are provisioning Archipelago on an as-needed basis. We'll find out if it's any better today. Okay, I'm going to give everyone another 15 seconds to put in their solution to this recurrence in Archipelago. So I see a question on the chat. What is the difference between space complexity and time complexity? When we look at time complexity, we're talking about the number of steps the algorithm takes. When we talk about space complexity, we're talking about how much space has been allocated. Okay, we're talking about literally how much space does the algorithm need, how big are all the arrays, all the memory that the algorithm actually needs. Okay? And we'll see that in a sec when we see how to get a better merge sort that doesn't use up so much space. Okay, so I'm going to call the Archipelago poll done. And what we see here is that, well, there was a sort of conflict between order n and order n log n. And in fact, the correct answer here is order n log n. Okay, it is unfortunately not order n because we've been allocating all this new space at every step along the way. Okay, so let us think about why that is. Okay, so order n log n is the answer. By the way, this recurrence should look familiar. This is the same recurrence we, of course, used to analyze merge sort in the first place, right? So this was the recurrence that we were solving. And as we saw last week, you can solve this recurrence by simply unrolling the recursion tree, okay? And again, these are the same, basically the same slides we had last week, except I've replaced time with space because it's the same recurrence. You start out doing this merge that allocates n space, and you have these two recursive calls that allocate, you know, s of n over 2 space. Each of those recursive calls is going to itself allocate an array of size n over 2 and do 2 recursive calls. Each of them is going to allocate some space of size n over 4 and do 2 recursive calls, and so on. And so we get down to a base case when we have an array of size 1. We add everything up. At the top, we've allocated n space. At the next level, we allocated n space. At the next level, we allocated n space, and so on all the way down. There are log n levels of this recursion tree, and so the total cost is n log n. Again, I'm going through this quickly because this is exactly the same as when we did the time analysis last class. Okay, great. If you simply implement merge sort naively, the way we've done here, it is going to be order n log n space. Okay, but of course, this is not the most efficient version of merge sort you get. I see a question in the chat about what if we sort in place, or maybe even what you mean in this case is what if we merge in place, which is a good question. Merging in place is a little bit tricky if you want it to be efficient. It's certainly a good question to think about how you would try to do an in-place merge. Okay, we're not going to do an in-place merge here, but I claim we can do better even without an in-place merge. In particular, what we're going to do is we're going to allocate a single array of size n, some temporary array, where we're going to use as our scratch space. And we're only going to use this one array of scratch space during the entire computation. And as a result, we're only going to need order n space. In fact, we're only going to need something like 2n space with a little bit of extra log n stuff in addition, per se, to keep track of the recursion. Okay, good. So we only want to allocate one temporary array. Let's see how we can do that. So now we have this temporary array, and we are doing our merge sort between some range of begin to end. Okay. As before, the way it works is we have these two recursive calls on the first half and the second half of our array. And in this case, in each case, we are expected to be sorting using this temporary array as our scratch space. Okay. And when the sort is done, A has the sorted half arrays in it. Okay. But we use the temporary array as scratch space. We didn't allocate any more space. Okay. Then comes the merge down here. And what the merge does is the merge is going to merge from A into the temporary array. Okay. So when the merge is done, the temporary array is going to have the sorted array in it. And then the last step we have down here is going to be copy from the temporary array back into A. Okay, good. So in this case, then we will not need to do any extra allocation in the merge. We only allocate this one extra temporary array and everything is good. Okay. No. Good. Sorry, I'm trying to clear the screen of the things I just drew on it. I'm trying to clear the annotations. Let's do that. Okay. No. For some reason, I cannot clear the annotations. Weird. Okay. Apologies for this delay. I'm trying to figure out why I cannot get the annotations to clear. Annotate, clear all drawings. There we go. All drawings cleared. Wonderful. Sorry about that. Sorry about the technical difficulties. Onwards. Okay, good. So now we end up with this recurrence. We end up with a recurrence where, at every step, we're doing these 2 steps of recursion, just like before. But now we only allocate order 1 extra space at every step, right? This order 1 is coming from whatever, some new loop variables or things like that. Okay, I'm not going to spend the time waiting to answer this because I really already said the answer. In this case, this recurrence has a solution of order n. Okay, good. So this certainly improves the space usage this way. Okay, but it turns out we can do a little better, right? So there's still a problem here. We still have this extra copying going on where we have to spend a whole bunch of time copying from our temp array back into our original array. That's annoying. We should be able to find a way around that. Okay. Well, here is a clever idea to get around that, a sort of clever use of recursion, that instead of just using the temporary array and copying back, we can switch back and forth between 2 arrays, which ones we're going to use as our temporary array. So we have initially 2 arrays, A and B. Okay. Initially, A and B both have copies of the unsorted array, and we're going to recurse all the way down to the bottom, alternating A and B at every step. Okay. And then as we unroll, we're going to merge first from A into B, then from B into A, then from A into B, and so on, switching the order of A and B at every recursive call. Now, this I think is pretty hard to visualize like this. It's a pretty sort of tricky recursive idea. Here's the way I like to think about it. So I talked before about this bottom-up merge sort. There was a reason why I talked about bottom-up merge sort. I think this is the easiest way to understand this idea of swapping the arrays back and forth. So originally in this bottom-up merge sort, you start with your array and you do your pairwise merging into a new array. And then you do the pairwise merging into a new array, the pairwise merging into a new array. And of course, you see that we need n log n space in total, right? There are log n of these levels, and each of them has n space. No good. But what we've just observed is that we don't actually need a new array at every level, right? We can merge, we can do our first pairwise merging from this blue array into this red array. And then we can do some pairwise merging from this red array into this blue array, and then some pairwise merging from this blue array back into this red array, and so on. At every step, we can switch the arrays that we are merging from A to B to A to B to A up the chain. Okay. And if we do it that way, then we only need 2 arrays in total, and we don't have any extra copying. Okay. So this is how you get from the sort of naive order n log n merge sort to a much more efficient order n space merge sort. Okay, good. So this is all I want to say about the space for a merge sort right now. I'm just quickly looking over to see if there are any questions that I should answer, either in the random questions or the chat. I see S of n is the max space used over all iterations. So S of n is the total space allocated for a call to merge sort of size n. Okay. I also see a question of where is the switching here? So the switching is happening at every level of the recursion. So going back a step to here, what you're seeing is that when we call merge sort A comma B, the recursive calls do merge sort B comma A. And the recursive calls that this does will be A comma B again. So the switching is happening at every level of recursion. Okay, let me see if there are any other questions here. Nope, I don't see any other questions. So we are going to keep going. So this is where we are so far. We've seen bubble sort, selection sort, insertion sort, and merge sort. Okay. The next sorting algorithm I want to talk about is QuickSort. It is another classic divide and conquer sorting algorithm. Okay. So we're going to look at QuickSort, look at a whole bunch of issues related to QuickSort, and then talk about how to analyze QuickSort using the tool that I'll call Paranoid QuickSort. Okay. So a little history lesson. You didn't know you were in history class here. QuickSort was invented by Tony Hoare in about 1960. Tony Hoare is one of the sort of famous computer scientists from the 60s, 70s, 80s, and so on. He actually won the Turing Award in 1980, which is the biggest award in computer science. He invented QuickSort when he was a visiting student at Moscow State University. And this must have been somewhat exciting. So he's British. And at the time, the Cold War was underway. And yet he decided that he was going to spend a year or a semester at Moscow State University. And while he was there, he was working on a machine translation system. He was working on how to translate things between English and Russian. And the sorting algorithms he had were too slow. He needed a way to sort his dictionaries so they could efficiently look things up. And things were too slow, and so he invented QuickSort as the solution to his problems. Okay, so this is the backstory behind QuickSort. Tony Hoare is famous for a whole variety of wonderful quotes, but one of them is here. There are two ways of constructing a software design. One way is to make it so simple there are obviously no deficiencies. The other way is to make it so complicated that there are no obvious deficiencies. The first method is far more difficult. So when you are pondering how to solve a problem on a problem set, keep this in mind. Okay, good. So QuickSort, as I said, it's a wonderful, elegant algorithm. It's very fast in practice. There are lots of optimizations out there. It's in place, so we don't need any extra space. It has good caching performance. It parallelizes well. It really is a wonderful algorithm. Okay. A little more history about QuickSort. It was invented in 1960, as I said. It took a little while for people to catch on and discover that it was so useful. But by the late 1970s, it had basically been adopted everywhere, especially when Unix decided to use QuickSort for its system sort as QSort. By this point in 1979, it was basically accepted by computer scientists that QuickSort was the way to sort. And then some time passed and some time passed. And around 1993, in the early 90s, a bunch of people noticed that it didn't always work as well as they expected. You found quotes like this: in the summer of '91, our colleagues Wilkes and Becker found that a QSort run that should have taken a few minutes was chewing up hours of CPU time. Had they not interrupted it, it would have gone on for weeks. Okay, part of this is it was 1991 and computers were a little slower then, but the other is that it turned out there were some problems. I'm sure you've had this writing code yourself. You write some code, you think it should work well, you start running it, and half an hour later you realize that something's not right. I've certainly done this before. In this case, they discovered that basically QuickSort was not working as well as they thought. And in particular, they found that there were instances that were taking n² time to run. And so Bentley and McElroy actually did a whole bunch of work optimizing and improving QuickSort to make it work better in practice. Okay, they wrote this famous paper called Engineering a Sort Function. It is an old paper from the 90s, but very much worth looking at if you're interested in the question of how do you engineer good software. Bentley and McElroy have wonderful ideas on how you actually take a simple algorithm and make it work well in practice. And a lot of that's encapsulated in this paper. Okay. Fine, so 1993, Bentley and McElroy solved the problem of QuickSort. QuickSort is done, said everyone. We've solved the problem, it's done. We can now teach it in our first year CS classes safely without having to worry about it anymore, right? Okay, of course, there's a problem. Every time we sit down to teach QuickSort, some punk in the front row of the class, back when we had in-class person, raises their hand and says, wait, what if we use more pivots? Don't worry about what that means, but someone always asks that question. And of course, being a good professor, we have an answer for that, right? It doesn't work. It doesn't work. I can prove it. I'll show you the theorem. Let's get back to the syllabus of the class, right? This is how we answer questions. Good. Fine. Doesn't work at all. Unfortunately, the punk in the front row doesn't always listen to you and says, let me try it. And then, wait a sec, it actually is faster. And this is exactly what happened. Around 2009, Vladimir Yaroslavsky refused to listen when we all told him that it was not useful to have more pivots, and he invented dual pivot quicksort. And amazingly, it was faster. It is now the standard use of quicksort in Java uses Yaroslavsky's dual pivot quicksort. It's about 10% faster. Okay. So anyways, I think this is a wonderful story because, and the story keeps going a bit. Then a couple of years later, those of us who do theory and analyze algorithms, the theorists caught up and were able to actually understand why it works better, right? So if you just do simple asymptotic analysis, there is no benefit, even though it is 10% faster. A couple of years later, Wild and Nebel were actually able to gain some deeper understanding of what's going on and why dual pivot quicksort really does seem to be faster. Okay, so the moral of the story, don't just listen to me, go and try it. Go be like Yaroslavsky, go out and write the code, run it, and see if it works. And if it does, figure out why. Okay. The other moral of the story here is that even classical algorithms, even those that were invented back in 1960, they change over time. They are not permanent, fixed, etched in stone. The quicksort that we are teaching in 5 years may be different than the quicksort I'm teaching today. So keep in mind that things change quickly. Okay. Good. So that's the history lesson about quicksort. We can actually now get to the algorithm. Who's going to do trio pivot quicksort? Yes. At this point, there's been lots of experiments now about the optimal number of pivots. You should go and see for yourself. There's a lot of controversy over that. Okay. Please don't write on the screen. Thank you. Okay. Good. So what about quicksort? Fine. So it's relatively easy to understand. It's a very simple divide and conquer algorithm. It is moderately hard to implement correctly. It is well known as a classic example of off by one errors. It's slightly harder to analyze, involves some randomized analysis. And then, as was found out, the fact that it took 50 years or so to get good implementations of it, it can be challenging to get the best possible performance out of it. Okay, good. Let's get on to the algorithm then. So here's, we talked about MergeSort at the beginning. In some ways, you can think of QuickSort as kind of flipping around MergeSort. So MergeSort first does 2 recursive calls and then does a merge. Well, QuickSort flips things around and says, let's first do our pre-processing, our partitioning in this case, and then do our 2 recursive calls. Let's first partition the array into 2 pieces, a small and a big piece. And then we can invoke the magic recursion theory. We can invoke our wishful thinking, as Martin Hertz would say, and do our recursive calls over here on the left and right half. Okay, so this is the basic paradigm between QuickSort. So you'll notice, of course, that in MergeSort the key step was merge. For QuickSort, the key step is partitioning. Partitioning is the most important and only interesting thing that is happening in QuickSort. Everything else is just recursion. Everything else is just boring. Okay, all the interesting stuff happens in your partition function. Okay, so what does the partition function do? Well, the idea of the partition function is to divide the input into items that are small and items that are big. Okay, so imagine you start out with some collection of items over here, some big collection of stuff. What you want to do is you want to take all the small things and put them on the left half, and all the big things and put them on the right half. Okay, and the thing in the middle, we're going to call that the pivot. Okay, so the pivot is the item which all the items on the left are less than the pivot, all the items on the right are larger than the pivot. That's what the partition function does. Okay, once you've done that, once you've partitioned things into things smaller than the pivot and bigger than the pivot, then it's just a matter of recursion. Then we just have to recurse on this side, and we are done. We have a sorted array. Okay. As I said, this is a classic divide and conquer paradigm. First, we divide, we partition the array into 2 subarrays, splitting things around a pivot. We then conquer by recursively sorting the subarrays, and we combine things together, which is a trivial do-nothings type of operation. okay? And so basically, all I need to talk about for the rest of class is the partition subroutine. Nothing else here is worth talking about. An efficient partitioning subroutine is what makes QuickSort work. Okay, so let's talk about partitioning the array then. Fine, there are basically 3 steps to partition the array. We need to choose a pivot. We need to find the items smaller than a pivot, and we need to find the items larger than the pivot. Okay, great. So here's an example. Let's say that we start out with 6 as our pivot. Okay, well, 6 is our pivot. We need to divide the array into things smaller than the pivot and bigger than the pivot. Here we have done that. Okay, we have 3, 4, and 2 that are less than the pivot. We have 9 and 8 that are larger than the pivot, and we've stuck the pivot right here in the middle. Okay, great. Then we can recurse on the left side. Let's take the first element here, 3 as the pivot. Great. We sort things into things less than the pivot and things bigger than the pivot, putting the pivot in the middle. We recurse on the right side. Again, here 9 is our pivot. We divide things into smaller than the pivot and larger. And well, this middle element here, the pivot, just comes on down. It stays in the same place. And we have a sorted array. Okay, so here's a question to think about. Here's a question to answer on Archipelago. The following array has been partitioned around some element. Which was the pivot that we chose for this array? Okay. Good. Run on over to Archipelago, see if it's working today, and see if you can guess what the pivot is. You can begin working on your sorting detective skills. Okay, I see a bunch of answers here. Excellent. In fact, I see that a good 3/4 of you, maybe a little more, have chosen 22. Excellent. 22 is the correct answer here. You'll notice that everything here to the left is smaller than 22, 18, 5, 6, 1, and 10. And everything over here is larger than 22, 40, 32, and 50. Okay. Here we have an array partitioned around 22. Wonderful. So let's see how the partitioning might work. So here on top, we have the array that we want to partition. On the bottom, we have the place we want to put the partition stuff. And let's imagine that we want to partition around 22. Okay, well, there's a simple way of doing that. We can basically just start and iterate through the array and take the small elements and put them on the left and the large elements and put them on the right. Okay, so for example, we can take 1 and put it on the left. It's less than 22. We take 6 and put it on the left. It's less than 22. We spend 40. 40 is bigger than 22. We put it on the right. 32 is bigger than 22. We put it on the right. 10 is less than. 18 is less than. 50 is bigger than. 40 is less than. And what are we left with for this very last slot? Well, this very last slot is going to be exactly 22. That's where we put the pivot that we started with. Okay, great. So here is some pseudocode for our partitioning algorithm. The pseudocode doesn't really matter. This is just going through and, well, go through every item. If you're less than the pivot, put it on the left side. If you're bigger than the pivot, put it on the right side. Okay, good. So as you recall, one of the things we've been talking about is how do we actually show that algorithms are correct? This partitioning algorithm is quite simple, but I think it is, again, an instructive example for how to use invariance. Okay, here's some claim you might make. This array B, when we're done, I want to claim this is partitioned around the pivot. I want to claim that our partitioning algorithm has done the right thing. Again, I know this is not rocket science, but it's good to think about how you would say this carefully. Well, there are 2 invariants that you might want to show here, right? You might want to show that for every I less than low, BI is less than the pivot. So if everything less than the low pointer is less than the pivot, and everything bigger than the high pointer is bigger than the pivot. And if you can show that, then you'll see that in the end, well, if every element has been copied from A to B, we have a properly partitioned array. Good. Okay. So next things next. Quick question here. What is the running time of this partitioning routine? Hopefully this should be an easy question. We've just come up with a simple partitioning algorithm. How long does it take? I will give everyone a couple seconds to go quickly put their answer in over at Archipelago, which appears to now be going slowly again. Oh, well. I will give it 10 more seconds and then I'm going to go on. Yeah. Okay, good. I see some answers. So I'm going to go on. And in particular, in this case, the partition function is always going to run in order and time. If you think about it, it just goes through and looks at each element once. It takes the element and copies it into the output array. It looks at each element once. Okay, here's the more interesting question. What are any problems with what I've done so far, or anything that can be improved? Okay, do you have any ideas for how we might do better? Again, there's a question Archipelago. Go put in your best ideas for what is wrong with this partitioning routine. Do you think we can make it run faster? Do you think we can make it better? Do you think we can make it, I don't know, tell me what's wrong with this partitioning routine. I'll let you think for a minute or two about how we might improve it. Okay, I see a bunch of people have put in their suggestions. I see a lot of suggestions about the pivot, about, pick the middle item as the pivot, pick some other item as the pivot, pick the whole bunch of stuff on picking on what to choose as the pivot. We're going to come back to how to pick the pivot. I'm especially interested in the partition function here, what we can do better. What else am I seeing here? Lots of stuff on the pivot. What about if there aren't unique items? I think that this partition function I've described should work even if we have non-unique items. Even if the whole array are 6s, I think this partition function should still work okay. Okay, what else do I see here? I see a comment about space. And do we need extra space? Good. That was the issue that I really wanted to get at here next, was this question of space. Let me just look through the other answers and see if there's anything else interesting. Unable to sort repeated elements. Again, I think the algorithm we've described would work for repeated elements. It just might not be fast. It is unstable. Is the algorithm I've described so far unstable? That's a good question. Why would this be unstable? I'm taking items in order and copying them down to the bottom array in order. And if they're identical, they're both going to be copied to the low side or both to the high side. On the other hand, I suppose they'll get inverted on the high side, won't they? So you are correct. This is not stable. This is not a stable partitioning algorithm. Good, because of the stuff on the high side. Excellent. Okay, but the issue that I'm particularly worried about here is the issue of space. And the question is there a way to do this without having to use an extra array? Is there a way to do this without having to copy everything into a new array? Okay, so we'd like an in-place partitioning algorithm. We'd like to partition this array around 22, but without allocating a whole new array. So let's see how we can do that. Here's one way you might do that. You have some low pointer on this side again, and here's our high pointer on this side. And our goal is going to be, just like before, put the low items less than low and the high items bigger than high. Okay, so we're going to go through and say, great. Well, we're going to move this side until we find something that's too big, something that doesn't belong on the left side. So 1 is less than 22. It belongs on the left side. We will leave it. 50, on the other hand, we want to move this pointer in until we find something that's too small, that doesn't belong on the right side. So for example, 50 is bigger than 22, so 50 is going to stay on the right side. Okay, so here we go. Let's see what happens. We move in our right pointer to 6 because 1 is less than 22. We move in our right pointer to 40 because 6 is less than 22. We get here to 40, we can't go any farther. We have to stop. 40 is bigger than 22. We can't put it on the low side of things, right? We can't let 40 get to the left of the low side. So let's hop on over to the high side over here. On the high side, 50 is bigger than 22, so we can advance. But then again, we have to stop. 4 is less than 22. We can't put 4 on the high side. We can't let 4 get to the right of the high pointer. So again, we have to stop. So here we are. We have our 40 and our 4. We can't go any farther. What do? Well, we can simply swap the 40 and the 4. Here we go. We swap the 4 and the 40. And now we get rid of our stop signs and we can keep going. Isn't that exciting? So 4 is now less than 22, so we can move on. Alas, we hit 30, 32, we have to stop again. On the right side, we can advance some more, but again, we hit 18, we have to stop. Again, we can swap the 32 and the 18. Great, then we can keep going. 18 goes up to 10, that's fine. 10 goes up to 32, that's fine. And now we are done. High is equal to low, so we are happy. We have correctly partitioned the array. Well, we've almost correctly partitioned the array. There is one more step that we have to follow here. We have to put the pivot in place. The pivot is sitting here, over here, hanging out on the left. That's, of course, not the right place for it to be in the end. So we're going to have to swap the pivot into the proper place, which is there. Okay, great. So this is our in-place partitioning algorithm. This is actually not the original partitioning algorithm that Hoare proposed. Tony Hoare had a different, somewhat more complicated partitioning algorithm that actually had some advantages to it, but tended to be a lot more buggy in practice because people struggle with implementing it without off-by-1 errors. And so this is actually, I think, the more commonly used today partitioning algorithm. Okay, good. So here is some pseudocode for the partitioning algorithm. What you'll notice is this is doing, again, I don't want to spend a lot of time on pseudocode here. In part, I put it on the slide so you can look at this later. But what you'll notice is that we are iterating through while low is less than high. We advance the low pointer as far as we can. We advance the high pointer as far as we can, and then we swap low and high. Okay, and we do that until low is equal to high. Once we're done with that, we can swap the pivot into place, and we are done. So this is assuming, of course, that the pivot is being stored in the first, array location, and I'm ignoring array out of bounds issues. See, ignoring array out of bounds issues because I am writing pseudocode. And of course, in real code, you'll have to be careful of things like this. Okay, great. Which is actually exactly the point I wanted to make now for a sec, is that this is, of course, all pseudocode. As you all know from your experiences with Java, writing real code is an additional challenge. And QuickSort in particular is notorious for off-by-1 errors. Back when I was getting jobs right out of college, it was a standard interview question to say, walk up to the whiteboard and please write QuickSort on the board. Because it was so common that no one could actually do it without off-by-1 errors, without getting the boundary cases wrong, that it was seen as a great interview test question. I suspect now enough people know that they've memorized how to do it in advance. But that tells you something about how easy it is to get wrong. So if you are writing your partition and QuickSort code, be very careful looking for off-by-1 errors. Okay. There's a question in the chat, did I memorize it? No, I didn't memorize it. I just claimed I just didn't know it. I wasn't a computer science major in college, but that's a whole nother story. I'll tell some other time. Okay, good. So last question. Last thing I want to talk about. We only have a couple minutes left here today, but again, as before, you might want to have a set of invariants so we can prove this actually does the right thing. How do we actually prove that our partitioning function is right? It's now a little bit more complicated, so it actually pays off a little more to think about the invariants. So here's a natural invariant that you might want. You might want to show that the thing that the high pointer is pointing to is always bigger than the pivot. That's useful, right? If you prove that, if you prove this is an invariant, then you will show that throughout the execution, all the stuff that's to the right of the high pointer also inductively is going to be bigger than the pivot. Okay, so initially this is true by assumption, and then you have to go through and show that the loop invariant holds. You'll have to show that at every step of the argument, it will still be the case that the high thing stays bigger than the pivot. Again, I wrote some text on the slides that you can look at later. I'm not going to go through that right now. Okay. Good. And so once you're all done, you can show things like these two invariants, that everything bigger than high is bigger than the pivot, everything less than low is less than the pivot, and then you are done. You then have a nice happy invariance that prove that your algorithm is correct. Okay, good. Wonderful. So that is the sort of the currently playing classic partitioning algorithm. Okay. Its running time is going to be order n, so that's nice. So it runs in linear time. It only has to look at each element once. It advances the low pointer, the high pointer. It scans through the array, order n time. We have successfully partitioned the array. Okay, good. Okay, so I think this is sort of the summary of QuickSort. There's a lot more to talk about regarding QuickSort that we're going to get to on Tuesday. In particular, we've talked so far about the basic divide and conquer approach. We've talked about partitioning. On Tuesday, we're going to get on to talking about how do we deal with duplicates in the array, how do we choose pivots in the array, what's the best way to choose a pivot, and we will then get to the randomized analysis. How do we analyze a randomized algorithm and show that it actually has the good fast performance that we want? Okay, so I think that is it for today. That's all we have time for. And that's what we're going to do next time. So have a good rest of your week. If you haven't had your tutorial yet, have fun in tutorial. And I will see you all on Tuesday. Thank you.
Thanks, Prof.